I hope you will understand my English. I will speak as clear as I can. Now, you see my name here. This is the Ukrainian version, and this is my version. My name is Dan, not Daniel. This is the only correction. Okay, so let us start. The subject I will be talking about is quasi-periodic material, a new definition in crystallography. And this is a subject that has emerged as a consequence of my discovery of quasi-periodic crystals. And I will tell you the science, and it will be very simple. Although it's a complicated science, I will make it as simple as possible so that even if there is a lawyer here, he or she will understand. Okay, so let me take you back to the mid-80s. And in the mid-80s, there were three surprising discoveries on the structure of matter and its properties. And these discoveries came year after year, and all three of them received the Nobel Prize. So this is quite an event. Now, the first discovery, was the discovery of quasi-periodic materials. And it came, the announcement came in 1984, and this is my name, and there were three more people, Ilan Blech of the Technion, Denis Gratias from France, and John Kahn from the United States. And this was 1984. 1985 came the discovery of fullerenes by Harry Krotter and his colleagues. And a year later, came the discovery of high-temperature superconductors by Alex Muller and George Bednorz. Now, when high-temperature superconductivity was discovered, there was no objection to the discovery. Everybody was happy that now we have materials that instead of cooling them down to liquid helium temperature, you can cool them down to liquid nitrogen temperature. This is less expensive and maybe more useful. Everybody was happy. When fullerenes were discovered, there was some objection to the model, and Harry Krotter tells me that there were about 6 papers objecting the model that he and his colleagues proposed, but that opposition died very soon. However, when quasi-periodic materials were announced, they met a lot of opposition from the top of the scientific community in the world. And that rivalry, or that fight against the concept of quasi-periodicity, lasted for 10 years, from 1984, the year of the discovery, to 1994, when the opposition stopped abruptly, and I will tell you why it stopped. So this is in the mid-80s. Now, in order to clearly understand what quasi-periodic materials are, we need to say something about order in crystals, about periodicity in crystals, and about rotational symmetry in crystals. It is very simple. First of all, order. So this is an ordered structure right here. Let's say that this is a two-dimensional ordered structure of atoms. And clearly you see that if I ask you to continue this in each and every direction, like in this direction or any other direction, you know how to do that because you understand the periodicity, you measure, you put another atom, another one. It's very easy. This is order. That's all we need to know for now. But this structure is not only ordered, it is also periodic. And because the structure is periodic, that means that there are equal distances between any 2 points, then every direction there is also periodicity in every direction. So you can see that there is periodicity here, and periodicity here, and periodicity here, equal distances in each and every direction that you choose. That's all about periodicity. What about rotational symmetry? Here I have the same two-dimensional structure, and I have added a little handle at the top, and I can rotate it. I can rotate this 90 degrees, and it looks the same. 180 degrees looks the same. 270 degrees looks the same. and back to 360, and every time it looks the same. And you can do it 4 times. This is why this structure has a 4-fold rotational symmetry. Okay, that's all for that. Let's say a few words about crystallography. Crystallography is the science in which we study crystals. And I must add that recently, and if there are people who teach or study biology here, you know very well that today we use crystallography not to study so much the structure, but to study each and every molecule. And we study now proteins, which are very complicated molecules, with the same technology that in the past we studied the structure of crystals. Okay, so what about crystallography? Modern crystallography started in 1912 with the seminal work of von Laue, a German scientist, who performed the first X-ray diffraction experiment. He was the first to perform X-ray diffraction of crystals, and he was the man who brought the science of crystallography into a modern science. Now, even the old Greeks, the ancient Greeks, had some good ideas about the structure of matter. They imagined that materials, crystals, are made from atoms. Atom is a Greek word, undivided, small parts that are not divided. Well, now we know we can divide them, but this was the Greek notion. And those atoms build the crystals, and it was a good idea. By the way, if you think that ancient people knew something about science, that is not the case. They understood very, very little about science, but they were right about crystallography. But nobody had the tools to prove that the idea of atoms which are arranged in an orderly manner, this is exactly what really happens. And in 1912, von Laue created the first X-ray diffraction experiment, and from there on, we had a tool which was developing fast, accurate X-ray diffraction to analyze crystals. And X-ray diffraction was the tool of choice of crystallographers. And over years, it became very, very precise. So we could measure exactly distances between atoms to high precision. And X-ray diffraction was the tool of choice, although there are other ways to study crystal. You can do neutron diffraction, you can do electron diffraction, but the International Union of Crystallography, this is the union of the people who are responsible for what is right and what's wrong in crystallography, they have declared X-ray diffraction as the tool of choice. And any other tool was not accepted for discoveries or for precise measurements. Okay, the crystals von Laue studies were ordered, and therefore crystals, but also periodic. And all the hundreds of thousands of crystals studied during the 70 years from 1912 till 1982, the year that I made my discovery, were found to be ordered and periodic. Hundreds of thousands of crystals were studied individually by tens of thousands of excellent crystallographers around the world. And all the crystals that they have found were ordered and periodic. And based on this observation, a paradigm was created. A paradigm is a definition which is not based on any solid proof, but based on many, many observations. So since all the crystals, hundreds of thousands of crystals that were discovered were ordered and periodic, then this was the definition of a crystal, and it was accepted by the scientific community. So what was this definition of a crystal? When I was a student, this was the definition. A crystal is a solid composed of atoms arranged in a pattern, periodic in 3 dimensions. A crystal is ordered and periodic. Very simple. Here is another definition from another book, the same meaning, different words. Atoms in crystals are arranged in a pattern that repeats itself. Repeats itself means periodic, in 3 dimensions throughout the interior of the crystal. This was the definition, and the science of crystallography was a mature science. Mature science is a science in which we think we understand everything. Nothing new can happen. Yes, of course, somebody can analyze a new crystal that they made in the laboratory or found in nature. But all the new crystals had a category. For instance, if the structure of a crystal was found to be DO19, which is some kind of a crystal, then we have a drawer in which we have 200 crystals with DO19 structure. Here comes 201, welcome, put it in the drawer, thank you very much. Nothing shocking was expected, and the science of crystallography was a mature science. Now, crystallography in 1982, which is the year of the discovery, can be manifested by a book by Charles Kittel, and I marked something in green. I know you cannot read this. This is why I enlarged it for you, and now you can. So, we can make a crystal for molecules. You can make a crystal for molecules, which individually, each molecule can have a 5-fold rotation axis. Each molecule can have a 5-fold rotation axis, but we should not expect the lattice to have 5-fold rotation axis. I showed you before a lattice that has a 4-fold rotation axis, but you cannot have 5-fold. And I could prove to you why we cannot do that, but there is no time to do it just now. But I can tell you a story that when I was a student at the Technion in Haifa in Israel, I took a class in crystallography during my master's degree studies, and one of the questions in the final exam was prove that 5-fold symmetry is forbidden, cannot happen in crystal. And you know what? I proved it. And I passed the exam, and this is why I'm here now. It's easy to prove. Is it wrong? It is correct for periodic crystals. Yes, in periodic crystal, you cannot have 5-fold rotation symmetry. But there are other crystals which are non-periodic, and this is my discovery. Okay, let's continue. These are atoms in diamond. This is high-resolution electron microscopy. Each white spot is a carbon atom, and this is diamond, and this is high-resolution electron microscopy. You can see the atoms there clearly. And you can clearly see that this is an ordered structure. Diamond is ordered, made of carbon atoms, which are ordered. And because there is ordered and periodic, there is periodicity in every direction. For instance, there is periodicity in this direction, periodicity in this direction, periodicity in this direction. Any direction that you choose, you find periodicity. The order of carbon atoms in diamond is periodic. The allowed rotational symmetries are 1, 2, 3, 4, and 6. 5-fold rotation symmetry, as well as any other symmetry beyond 6, is forbidden in periodic structures. So what are the periodicity that are allowed? 1, 2, 3, 4, and 6. No 5, and nothing beyond 6. It is true for periodic crystals. Can let me take you now to a diffraction pattern from periodic crystals. Diffraction pattern can be X-ray diffraction pattern, electron diffraction pattern, neutron diffraction pattern. Here I show you a diffraction pattern from electrons. So this is an electron diffraction pattern. And what happens in the electron microscope is the following. You have an electron beam that comes usually from above. You hit a specimen. Let's say that this is a specimen. The specimen is very thin, so the beam can go through. How thin? 1/10 of a nanometer. 1,000 angstroms is good enough. So the film is thin enough for the beam to go through, electron beam to go through. So there is a central beam that hits a phosphorus screen in the center, and the rest of the beams are diffracted sideways. by the rules of diffraction that were determined by the Bragg father and son. We shall not go into that. So this is the diffraction, but this point here, the fat point here, is the transmitted beam, and all the rest of the beam are diffracted beams. Okay, very simple. Also, you can see that there is periodicity of the diffraction peaks in the reciprocal space. So what is the reciprocal space? While the atoms exist in real space, this is the space where we live, the real space, where most of us live in real space. And the diffraction pattern lives in a mathematical space which we invented, which is called the reciprocal space. And we invented this reciprocal space in order to understand what we see in the diffraction pattern. Right? So we are now at the reciprocal space, and there is periodicity of the diffraction peaks. You see that there is periodicity, and you can see that there is periodicity in this direction, and periodicity in this direction, and periodicity in this direction, any direction that you choose. Like in the real space, also in the reciprocal space, there is periodicity. And therefore, the rotational symmetry that are allowed are 1, 2, 3, 4, and 6-fold, oops, exactly like in the real space. No 5-fold rotation symmetry, and nothing beyond 6-fold is allowed in the diffraction pattern from periodic crystal. It was true, it is true. So, and then something very interesting happened. The International Union of Crystallography, I want to tell you something about the International Union of Crystallography. It is based, it's made of mathematical crystallographers. These are no-nonsense people. Everything has to be defined from the very foundation, from the very basic. This is high mathematics, precise mathematics, and everything has to be very, very clearly defined, like mathematicians do. And then this no-nonsense body changed the definition of a crystal. And now, this is the new definition of a crystal. And we will read this definition slowly, because I want to show you that this definition is like a poem. It is very surprising that this definition of crystal comes from a hardcore scientific body like the International Union of Crystallography. Let us read this and see what it says. It doesn't say crystal is. No. By crystal we mean. By crystal we mean any solid having an essentially discrete diffraction diagram. Essentially discrete diffraction diagram. And by aperiodic crystal we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. This soft, humble definition comes from the International Union of Crystallography? Yes, this is the new definition of crystal. What happened? Why do we need a new definition of a crystal, and why it is so humble? So now I begin my talk. Up to now, it was introduction. 1982 was the 70th birth of crystallography. Remember, crystallography von Laue in 1912. So 1982 was 70th birth of crystallography. And this was the year that quasi-periodic crystals were discovered. Now, in order for you to understand what happened in the day of the discovery, in the hour of the discovery, I will take you to my laboratory in the United States, where I spent a sabbatical. I was there for 2 years sabbatical from the Technion. At the Technion and in other universities in Israel, after 6 years of working, you can take a year or two of sabbatical and go to work somewhere, which is excellent, because then we create communication for a long time with other scientists in good laboratories around the world. We create networking. This is wonderful that they allow us to go for 2 years or 1 year of sabbatical. So I was there at National Bureau of Standards. This is in Maryland, near Washington, D.C. And I was studying rapidly solidified metals, materials, My project was sponsored by DARPA in the United States, and the subject was developing new aluminum alloys for aerospace applications. You see, we scientists always do this. We make a proposal which sounds very applied, but we really spend part of the time doing very basic research. What does it mean? It means the following. I'll give you an example. In this case, I started to prepare new alloys based on rapid solidification, because this was my mandate. You take a metal, you melt it, you squirt it onto a copper rotating wheel, and it cools very rapidly. When you do this, you create metastable structures, not thermodynamically stable because of the fast cooling. So I prepared alloys of aluminum, 1% manganese, can have good applications. 2% manganese, yeah, maybe good. 5% manganese, possible. 10%, no. It's brittle, it breaks. But I continued because I was interested in the structure. I made 10% manganese, aluminum 15%, 20%, 25%, 30%, 35%. It is so brittle, you touch it, become powder. But it was very interesting. And there, in the alloy that contained 25% manganese, something totally new was observed. And this is really the subject of my talk. So, but let's go through this. So I will show you my NBA, National Bureau of Standards. TEM is transmission electron microscope. My logbook, these are notes that I make for myself. And my advice for the young students among you, and I see quite a few of you here, which is excellent, when you make an experiment or when you make a calculation, if you're a theoretician, write it down in a notebook. You may remember your experiment for the next week, but you will not remember your experiment next year. Write down in a logbook. Have a good, proper notebook, right? Write down everything you do, because some of it, one day, may be very important, such as this page in my logbook. So this is the page, and I must apologize. These notes were not meant to be seen by you. These notes are for myself. But it became history, and now I show this page. So what does it have? It contains a lot of information. Here is the date. April 8, 1982. And if the people in the back cannot see it, blame the organizers here that they don't have larger screen. I apologize for them. So this is the date, April 8, 1982. This is shortly after I arrived to my position there. The alloy that I was studying was aluminum, 25% weight manganese, and it was rapidly solidified. It doesn't say here because I was working only on rapidly solidified material. This number is the plate number. In the electron microscope, you took pictures, by the way, on glass plates those days. Now it goes directly to the computer. But those days, we took pictures on glass plates, and then we had to take them out to the dark room, develop them, fix them, dry them, print them. It was an occupation. Nowadays, you push a button, it's in your computer. Modern world. Okay, so this is the plate number 1720. There are many before and many after. SAD is selected area diffraction. It's a diffraction pattern. And another diffraction pattern. And this plate is 28K, meaning it's a picture, real space, of what I see in the microscope with magnification 28,000 times. K is 1,000. Electron microscope has very high resolution, and therefore we need very high magnification so that our eyes will see what the microscope can see. By the way, for your general knowledge, the only role of magnification in any microscope is to match the resolution of that microscope with the resolution of our eyes. So if the resolution of our eyes is about 1/10 of a millimeter, and the resolution of the microscope is 1 angstrom, then the ratio is the magnification we need, in this case, 1 million times. But so 28,000 times is a low magnification for the electron microscope. So I take more and more pictures, and then picture number 1724, I look at this picture and I said, wow, that's interesting. What's going on? I will show you this picture. And then I said, well, I must take a diffraction pattern. I take a diffraction pattern of the same crystal. I look at it and I write tenfold with 3 question marks. Tenfold rotation symmetry. Cannot be. Later on, I realized that it is really 5-fold, not 10-fold. But you cannot tell by looking at the diffraction pattern. And then I continue to perform experiments to find out what I have. And I'll tell you what I thought I have. So I look at this picture and I say, that's interesting. So what's interesting? Now, this is Mr. Archimedes. And the story tells us that when he discovered the famous law of Archimedes, he jumped out of the bathtub shouting, Eureka! We don't do that anymore. Mainly because who has time to take a bath? We take showers. But today, usually, when we make a discovery, we say, that's interesting, or, hey, what's going on here? This is our reaction, rather than, but those days they had time to take a bath. Anyway, this is the picture that I said what's going on. So what's special about it? What you see is a polycrystalline material. It means that it's a material that is made of many small crystals. Most materials that we use that are crystalline are polycrystalline, like the steel bars on your chairs or the screws on your chairs. They're polycrystalline, are made of small crystals. The ceramics that we are using are polycrystalline. It's made of small crystals. Only rarely do we use single crystal, like for the silicon industry. We use large single crystal. So these are small. Here is one crystal right here. Here's another one. Here is another one. And this is the size. This is 0.5 micron. So the crystals are less than 1 micron in size. They're not small, they're not large. But some of them are interesting. And this is what caught my eye. What is interesting? This crystal is pitch black, very black. This is very black. This is very black. Now, what does it mean to the electron microscope specialist? It means, and this picture is taken with a transmitted beam. And that transmitted beam has almost no intensity. It means that all the energy goes to the diffracted spot. And I have never seen before a crystal that diffracts so heavily, like this crystal, which is totally black, no intensity. So I say, well, that's quite interesting. What is the diffraction pattern from this? I take a diffraction pattern, and this is how it looks like. This is a diffraction pattern. I look at the diffraction pattern and say to myself, you know, when you do electron microscopy, today you don't need to be in the dark room because you look at a computer screen. But those days, you look at phosphor screen, and the room is totally dark, and you sit there by yourself for a whole day, and I love it. I love it. Nowadays, I don't have time for that, regretfully. Anyway, so this is the diffraction pattern. So what is the rotational symmetry? So I start to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, cannot be. 1, 2, 3, 4, 5. And I write in my logbook tenfold with 3 question marks. And as I said, this is really 5-fold. But in order to know that, I had to do another experiment called Kikuchi pattern. We should not go into that, but this is really 5-fold. But you see, not only does it have forbidden symmetry, periodicity is lost. There is no periodicity. See, take a distance from here to here, for instance, and you multiply it by 2, this distance by 2, you are here. And there is nothing there. No periodicity. It turns out that the ratios, this distance to the center divided by this distance to the center, gives us the Fibonacci number tau, which is an irrational number, 1 plus root 5 divided by 2. This cannot be found by experimenting, by measuring. You cannot have an irrational number by dividing two numbers by one another. This came from theory later. But no periodicity, five-fold rotation and symmetry, and no rational numbers anymore. Irrational numbers came into the science of crystallography. What's going on? When I discovered this, I did not know what I have. I thought that I have a twinned structure. Now, before going into that, I'll show you other different. You see, in the electron microscope, you can tilt your specimen, and you can rotate it in a goniometer. So you can take diffraction pattern from this position, this position, this position, any position you want. So these are the main diffraction patterns that I have taken. Five-fold rotation symmetry here, two-fold here, five-fold again, and 5, 3, 2, 3 again. These are allowed. This is not allowed in periodic crystals. But the periodicity disappears in all of them. Okay, this is what I thought I have. Now, this is diamond. This is a periodic structure, not quasi-periodic structure. This is diamond. These are pictures that I took a long time ago. And what you see here, this structure is twinned. I will explain. See, this is a single crystal. Here's another single crystal. Here's another one, another one, another. There are 5 of them. And there are boundaries between them, okay? Marked in red. This is boundary between this crystal and this crystal. This boundary is between this, and so on. But these are not just general boundaries in which the atom meet in any direction. They are meet in a very special angle. So that if you look at this plane of atoms, it continues here, like a mirror image, right? And this one here continues here, like a mirror image. And this one here, and so on and so forth. So these are very special boundaries called twin boundary. Now, why did I think that this is what I have? Because of the following reason. You see, if you take a diffraction pattern from here only, then you have a periodic diffraction pattern, because it's a periodic structure. If you take diffraction pattern from here, from this one, you have another identical diffraction pattern, but rotated 72 degrees. 360 divided by 5, 72 degrees. And if you take diffraction pattern from this, you have another one, again, rotated 72 degrees. So if you take a diffraction pattern of all 5 of them together, then you have superimposed diffraction pattern. 1, 2, 3, 4, 5. And obviously, it will have 5-fold rotation symmetry. But it comes from 5 crystals, not from 1. So I said, OK, I must have a twin structure. And this is why I have this 5-fold rotation symmetry. I spent the whole day looking for these twins, couldn't find them. There were no twins there. I knew there were no twins there in day 1. Why do I mention it? Because later on, when the fight against quasi-periodicity started, people said, these are twin structures. I said, no. I know from day 1, no twins there. I know it for sure. It's something else. Right? So this is why I mention it now. OK. OK, we don't have to dwell too much on that. 1984, I came back to the Technion, and then I published with my colleague Ilan Blech, a professor at the Technion at the time. We sent a paper for publication, and it was called The Microstructure of Rapidly Solidified Aluminum-6 Manganese. Aluminum-6 manganese is literally aluminum-25 weight% manganese. I sent this paper to a journal called Journal of Applied Physics. Some of you know this journal. Quite famous. Those days, we did not have computer or computer communication. So, and also, the young amongst you will never believe it, scientists could not type. We could not type. We had secretaries that typed what we gave them by handwriting. We wrote papers in our hands. The secretaries typed them. If they made mistakes, they typed them again because it was not easy to erase mistakes on the typing machine. And we corrected it, they typed it again, we corrected it, and finally we said, this is fine. So I printed it on a paper, put it in an envelope, put a stamp on it, and wrote nicely the address of Journal of Applied Physics and sent the paper to them. 2 weeks later, I received an envelope from them with a letter, and my paper is inside. Thank you very much, Dr. Shechtman, for your contribution to our journal. We have decided not to send it for review because we don't think it will be interesting for the community of physicists. Okay. So I took the same paper, put a stamp on it in an envelope, and sent it to another journal called Metallurgical Transactions. They accepted it and published it. But they published it 8 months after I sent it to them. It's a slow publication. In the meantime, I came back for the summer of 1984 to NBS. I was there every summer. And my host, John Kahn, looked at the paper. I asked him, what's wrong with this paper that it was rejected? He looked at it and he said, let's do something completely different. And he proposed to send a paper which includes only my observations from the first week in which I was working 2 years before. So we did that, and we added 2 more names, and this is paper number 2, and this is my name, Ilan Blech, Denis Gratias, and John Kahn. Denis Gratias is the 4th person. He's a French mathematical crystallographer, very talented young fellow, not young anymore. At that time, he was very young. And we wrote another paper, and we sent it to PRL, Physical Review Letters, and it was published in a few weeks. So what really happened is that the second paper was published first, and the first paper was published second because it was published a long time after the first one. The publication came in November 12, 1984, just before the end of the year 1984. When this paper appeared in printing, hell broke loose because I started to receive telephone calls, email from all over the world. Danny, we have it, we have it. People repeated my experiments in a few days. I wrote exactly how to do what I did. They repeated my experiment, received the same results, and from there on, we were a fast-growing community of avant-garde, young, ambitious scientists who took my discovery and made it into a science. It was a very fast-growing science, and it was an amazing period. And people joined from all over the scientific world, from many countries, and the contributions started to stream into the scientific literature. There were tens of articles, then hundreds of articles, then thousands of articles published. Very, very quickly, it was a huge science. I made a discovery on 3 materials. I published it only on aluminum manganese, but I noted there that it exists also in aluminum chromium and in aluminum iron. But they discovered hundreds of such materials, and they studied their properties, and they made the thermodynamic calculation. How can it happen that we have structures which are not periodic? And so on and so forth. And it was an amazing, amazing period. Okay. Now I want to explain 2 terms for you in order for you to understand what's going on. First of all, icosahedral symmetry. What is icosahedral symmetry? So first of all, what is an icosahedron? Icosahedron is a platonic body, and this is the shape of the icosahedron. And many of the quasi-periodic crystals have icosahedral symmetry, and some others have other symmetries. And the icosahedron has 6 5-fold axes. If you put your eye here and you look from here to the center, you'll see that there is a 5-fold rotation symmetry, right? If you put your eye here, there's another 5-fold rotation symmetry. Here's another one. Here's another one, another one, another one. 5 plus 1 is 6. This one here is just the negative of that, so it doesn't count. So there are 6 5-fold, 10 3-fold. This is a 3-fold rotation symmetry. You can turn it 1/3 of a turn, and it will look the same. So this is 3-fold. If you put your eye here to the center, you'll have a 2-fold. So this is the icosahedron. And my set of diffraction patterns and the angles between them were exactly icosahedral. So this is why we called it the icosahedral phase, because it has icosahedral symmetry. So this is the icosahedron. Now, you can also look at a football and notice that it has icosahedral symmetry. I don't know if you ever looked closely to a football. I'm sure many of you did. It's made of patches, pentagons, and hexagons, right? It's like that. And if you look from here, you clearly see 5-fold rotation symmetry. You can clearly see 2-fold here, and you can clearly see 5-fold here. And I doubt that even the best team in Ukraine know that they play with icosahedral symmetry. I really doubt it. Well, anyway, this is about icosahedral symmetry. What is quasi-periodicity? This is the main question. What is this? We have, in order to understand quasi-periodicity, I have to take you back to the 13th century. That's a long time ago. And the best mathematician of that period was Leonardo Fibonacci de Pisa. He was the greatest mathematician of his time, and probably hundreds of years later, he was still the greatest mathematician. And he had the first experiment to show what is quasi-periodicity. And in order to understand, this is, by the way, a drawing of him. Look at these eyes, amazing. And this is the picture, a photograph of a statue that has been erected in Pisa in his memory. It's there. If you ever visit Pisa, you know there is the inclined tower of Pisa. And just behind the Tower of Pisa is the graveyard under a roof, very small, under a roof. And this statue is there in that little graveyard. So in order to understand quasi-periodicity, I have to take you back to the experiment that Fibonacci offered. And these are called Fibonacci rabbits. So let's follow his experiment, and you will start to understand quasi-periodicity. It's fun. So here we have quasi-periodicity in one dimension, and it's based on Fibonacci rabbits. So what are Fibonacci rabbits? Let's say that rabbits multiply, and only female rabbits are needed for multiplication. No fun. So here in the first month, we have one female rabbit. And in the next month, in month number 2, she has a little baby rabbit. In the 3rd month, she gives birth to another little one. Sorry, she gives birth to another little one. And this little one has to mature 1 month before it can reproduce. These are the rules. So from here on, everybody can continue this. So in the 4th month, month number 4, this mother gives birth to a little one. This little one matures, and this mother gives birth to a little one. In the next month, this mother gives birth to a little one. This little one matures. This mother gives birth to a little one. This mother gives birth to a little one, and this one matures. Okay, so from now on, you can continue this list forever. That means that there is order. The very fact that you know the rule, how to do it, is order. But, by the way, I stopped it here because this was the end of the page. I couldn't continue anymore. Now, let's look at what we have. We have, by the way, these are the number of rabbits in each month. So we have 1, 2, 3, 5, 8, 13, 21, and so on. I will tell you the rule. But let's look at this line here. You see, we have large, small, large, large, small, large, small, large, large, small, large, large, small, large, small. There is no motif of any size that repeats itself periodically. None. It's ordered, but there is no periodicity. This is quasi-periodicity in one dimension, along a line. So Fibonacci rabbits are quasi-periodic set in one dimension. Okay. But now that we visit Mr. Fibonacci, let me tell you a couple of more things, because everybody needs to know general knowledge about Mr. Fibonacci di Pisa. By the way, his friends called him Blockhead. He was so bright that his friends called him Blockhead. I never understood why. Well, anyway. Okay. These are two very simple equations. The first one means that the number of rabbits in each month equal the sum of the rabbits in the previous month. So an equals an minus 1 plus an minus 2. 3 is 1 plus 2, right? 8 is 5 plus 3. 13 is 8 plus 5. So 8 plus 13 is 21. The next one will be 34. The next one will be 55, and so on and so forth. This is equation number 1. Equation number 2 tells you the following, that if you continue n to infinity, very, 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 very many, right, to infinity, then the ratio of the last one divided by the previous one, the ratio of the number of rabbits in the last one divided by the previous one, will give you an irrational number, which is 1 plus root 5 divided by 2, 1 plus 6, 1, 8, 0, 34, and endless digits behind it, and this is called the Fibonacci number, and it is an irrational number. It is a very famous number. Because this ratio, people say that this ratio has some aesthetic value, and they call it the golden ratio. Now, never argue with people of aesthetics. Okay, just agree with them. If somebody claims that they know aesthetics better than you, fine, no problem. So if you look at the Mona Lisa picture, then the ratio of the distance between her eyes and this is they tell you that it's Fibonacci number tau, which of course nonsense, but don't argue with them. Okay, so these are Fibonacci number, quasi-periodicity in 1 dimension. What about 2 dimensions? By the way, he published it in the year 1202, just the beginning of the 13th century, in the book called Liber Abaci. By the way, this is interesting to know. Liber Abaci is a book that was not dedicated to this at all. This is just a chapter there. The book Liber Abaci was written to convince the merchants of Pisa not to use Roman numerals for their calculations, but to use the the number that came from India that we use today for their calculation. All right? And so what seems today to be very simple, and every first grade child can make calculations, those days it was very difficult because they were using the Roman numeral, and it's terrible. So this was the reason for this book. Anyway, what about 2-dimensional quasi-periodicity? We have to go to Penrose Stiles. Now, Penrose is an eminent British scientist living in our times, really one of the greatest scientists of our times. And he is a physicist, he's a mathematician, he's a philosopher. He's great. And he designed the Penrose tiles, which are 2 tiles, 72 degrees, 36 degrees. If you join them according to certain matching rules, then you have Penrose tiles that have 5-fold rotation symmetry. If you take a diffraction pattern from this, it will show 5-fold rotation symmetry, and it is not periodic. There is no motif of any size which repeats itself periodically. This is quasi-periodicity in 2 dimensions. The man that shows that this diffracts, this will give you 5-fold rotation symmetry diffraction pattern, is another British scientist. He is a crystallographer named Alan Mackay. So both of them are a team, a wonderful team, that showed quasi-periodicity in 2 dimensions. And what about 3-dimensional quasi-periodicity? Well, these are quasi-periodic crystals. And this was taken by one of my students in my laboratory. You see very nice 5-fold rotation symmetry facets. Okay. Enough of it. Now, because you are such a famous university and you are such bright students and teachers, I would like to take you now to something very, very interesting, but you will have to employ your mind to follow me. It's fun. And what I'm going to show you is something called cut and project. So what do? I will explain and then I will do it. I take a high-dimensional space. Don't faint. It's not so complicated. Make a cut and projection of the high-dimensional space into a lower-dimensional space, and from periodic structure, I create quasi-periodic structure. I know, but I'll show it's so simple. Let me drink some water. That was good. Okay, so first I take a high-dimensional space. How high? I'll make it simple for you. Two-dimensional space is high enough. Already simple, right? This is periodic, right? Let's assume that in every intersection, there is a mathematical point. Mathematical points mean a point with no dimensions, right? Okay, so we have mathematical point here, and here, and here, everywhere. And now we make a cut. Remember, cut and project. Now we make a cut. What is the cut? It's a strip. I create a strip that starts in this point, and goes in this direction. So the tangent of alpha is not just any direction. I chose the tangent of alpha to be the Fibonacci number tau. Oh, okay. All right. So tangent of alpha, what's going on? Tangent of alpha, I'll come back. Tangent of alpha is the Fibonacci number tau. That's very thoughtful. That means the following. Let me say something, and I hope you all understand. It means the following. Because the tangent of alpha is an irrational number, then it means that if I start from a lattice point here, this line will never, ever meet any other point. Never. Why? Let's say that it met a point. Let's say that it met this point here. It doesn't. It's near. But let's say that it did. Then the tangent will be this divided by this, which is a rational number. But I sent it to an irrational number. The tangent is irrational. It will never meet any other point. Okay. Now, I take something that doesn't work well. Well, I don't know what's... Okay, we are back into reality. Okay, so this is the tangent. Now I take all the points inside and I project them onto this line. I project them onto this line. Okay? This point projected here, this projected here, this here, and so on. So now let's look at what we have received. We have large distance, large, small. Large, large, small. Large, small. Large, large, small. We created the Fibonacci series, which we know is a quasi-periodic array in one dimension. So what did we do? We took a periodic array in 2 dimensions, we made a cut and projected it, and we received a quasi-periodic array in a lower dimension, in one-dimensional space. Now, mathematicians don't bother with this. They take a 6-dimensional space, they make a cut in it and project it onto a 3-dimensional space, and from periodicity in 6 dimensions, they receive quasi-periodicity in 3 dimensions, which is our world. So they, and maybe you have mathematicians here that can do that, it's fun. They can take any periodicity in 6 dimensions, make a cut and project, and invent quasi-periodic 3-dimensional arrays that either exist in nature or not. Some exist, some not, but there are possibilities. Enough of the cut and project, but I want to show you now another experiment which bears contact to reality. I don't know why it does that. Okay, I bring the red lines now, okay? The red lines are almost like the black lines, but not quite, you see? Because I made the red line to meet this point here. And therefore, the tangent of alpha is periodic. This is 11 divided by 7. It is close to being quasi-periodic. Quasi-periodic is 1.618. 11 divided by 7 is 1.571. Very close, but it is periodic. And the unit cell is very large, from here to here. This is the periodicity. This is the first time it meets a point. And there will be a next time there and a next time there. There are materials like this that exist. There are many materials with very, very large unit cell, many of them, which are almost quasi-periodic, but not quite. These are called approximants. There is a large series of materials that are called approximants. They are very proud to be almost quasi-periodic, and they have very special properties. They are studied by many, many scientists around the world. Enough of these materials. Now to the story. No more science now. You see, the first years that I started to talk about quasi-periodicity, well, actually, I talked about strange materials with five-fold rotation symmetry diffraction pattern and irrational numbers and so on. The people in my vicinity had different reactions. My host, John Kahn, was positive. He said to me several times, Danny, my friends call me Danny. He said, Danny, this material is telling us something, and I challenge you to find out what it is. This was a good reaction. He didn't solve the problem, but at least he was positive towards it. The negative reaction was on the other side. So this was good. A bad reaction was that of my group leader, who came to my office one day, smiling sheepishly, putting a book on my desk, X-ray diffraction or X-ray crystallography, saying, Dr. Shechtman, please read this book, and you'll understand that what you're talking about cannot be. And I said, you know, I know this book. I don't have to read it. I teach at the Technion. I'm telling you, my material is not in the book. Took the book back, came back several days later and said, Dr. Shechtman, you are a disgrace to my group. I cannot have my name associated with yours. Please leave the group. So I left. Now, don't faint. It didn't mean anything very practical. I didn't have to leave my office or my laboratory, but instead of reporting to his secretary, I reported to another secretary of another group leader who adopted the scientific orphan, and life continued. But this was the range of reaction, from very positive to very negative and everything in between. Now, if you want to see how I felt during those years, it was something like this. Okay, so this was from the day of the discovery to the day of the publication, 1984. Then, from 1984 to 1987, there was another major rejection, and it came from a serious body of the International Union of Crystallography. I want to remind you that when I started to talk about my project, I told you that the tool of choice was X-ray diffraction, not anything else. It was precise, it was excellent. But quasi-periodic materials were very small. The crystals were very small. And if you took a diffraction pattern from many crystals, you cannot see the rotation symmetry, because instead of points, you have rings. And you don't see the rotation symmetry, and you cannot prove that it has five-fold rotation symmetry. So they told us, hey guys, we need X-ray diffraction pattern from a single quasi-periodic crystal. We could not give it to them because our crystals were too small. But in 1987, my colleagues in Japan and in France created large enough crystals, quasi-periodic, to take diffraction pattern by X-rays from one crystal, and they sent me the pictures, and in 1987, I went to a meeting in Perth, Australia. This is on the west coast of Australia, of the International Union of Crystallography, and I showed these pictures, X-ray diffraction pattern from quasi-periodic. These were the first pictures. And we have, I don't know if you can see it, we have five-fold rotation symmetry, three-fold, and twofold here, beautiful pictures. And when I showed this picture in my talk, the community said, okay, Lenny, now you're talking. And they formed a committee that redefined crystals several years later. So this was a major acceptance. So you may think, okay, hey, now the international crystallography accepts your finding. Who will object? Not so fast. Because then there was Professor Linus Pauling. Now, Professor Linus Pauling was arguably the greatest chemist of the 20th century. He was really an eminent scientist. He was the head of the American Chemical Society. He was an idol. He was one of the most famous scientists of the 20th century. And this man was staying on the stages. By the way, he was a very flamboyant speaker. He could speak to the masses. And he said, Danny Shechtman is talking nonsense. There are no quasi-crystals, just quasi-scientists. And everybody was cheering. He had hundreds of thousands of followers. When we started these arguments, I was there, and he was like the sun in the sky. And this debate continued for 10 years, from 1984 to 1994. And over that time, things happened. We started this way and ended this way. Because there were more and more supporters, and in 1994, he stopped arguing before he died, because he died. Okay, it's not funny when somebody dies. Well, anyway, so this was the end of arguments. And so after him, there were no rejection and no objection. Okay, I want to sum up with a few things. Number one, I want to mention a few people who made seminal contributions. I mentioned them already, but let's put them in order. Roger Penrose and Leonard Mackay, Penrose tiles and Leonard Mackay, who showed the five-fold rotation symmetry in the reciprocal space of Roger Penrose tiles. Ilan Blech, Denis Gratis, and John Kahn wrote the first paper with me. And Dov Levine and Paul Steinhardt are two scientists who made a model, but it's different than the Ilan Blech model. Their model is a mathematical model of tiling based on Penrose. Ilan Blech model is building the icosahedral structures from icosahedral joining in space. These are two ways of looking at the same phenomenon. Okay, let me show you something interesting because you're such a wonderful people. You see, this is a very interesting chart. It was written by hand by a friend of mine who died recently, Bob Schaefer, in the United States, and he took it to lunch with me, and I confiscated it from him, and this is why we can see it. Otherwise, he would throw it to the garbage. So what does it say? It's very interesting. N is the number of pages in the bibliography. What is the bibliography? We hired a secretary who collected all the papers on quasi-periodic crystals that appeared in the world. She printed them, she filed them. We had a library, many drawers of papers, and she created a bibliographic set. I mean, you could go to a paper in her notebook, and every page in the notebook contains maybe 20 papers, like bibliography, okay? So every page contains maybe 20 papers. So if you have one page, 20 papers. If you have 10 pages, 200 papers. So N is the number of pages in the bibliography, right? So he counted the number of pages in the bibliography and made a chart of 1 over N. So when 1 over N is 0.1, it means that N is 10. It means that there are 200 papers. Right? That's what it is. And as we go down, there are more and more and more papers. So he counted them in February, and in March, and in April, and I came there in July. So this is the last one here. And like a good scientist, he connected them with a straight line. And to our horror, we understood that in December of 1986, the number of papers on quasicrystal will reach infinity. Here's the proof. Well, it didn't happen, but the feeling was that the world is really exploding with activity around us. This is just an anecdote. Okay. Whereas before order was synonym to periodicity, now we know that order can be periodic and it can be quasi-periodic, and there are no arguments about that anymore. I want to, if we have time, to give you time to ask questions, but I will ask the first question and I will answer it. And then you, if we have time, you can do that too. So my question is very fundamental. Why is it that quasi-periodic materials were never discovered before 1982? 70 years of crystallography, tens of thousands of eminent crystallographers study crystals all over the world, and nobody saw quasi-periodic crystals. Why? Why is it? Is it because they're very rare, and I stumbled upon one of them? Or is it because they're not stable thermodynamically? You touch them, they disintegrate or transform? Or is it because they are very difficult to make, and I, with my magic finger, managed to make one of them? Or maybe they are made of rare elements, praseodymium, gadolinium, and a touch of zinc? Why? What is the reason? So let me answer that. Are they rare? No. They are not rare at all. There are hundreds of them. There are hundreds of such materials. Somebody could have discovered them because there are so many of them. Here was a partial list, very small list of the hundreds based on aluminum alone. So aluminum, cobalt, aluminum, chromium, aluminum, iron, this binary, ternary composition, very abundant. This is not the reason they were not discovered before. They are available. Are they not stable? Many are not stable, but what does it mean? It means that if you heat them up to 400 degrees C or thereabout, they will transform into a periodic structure, from quasi-periodic to periodic. Atoms will shift and they will transform. But at room temperature, they're stable. And more than that, there are some who are stable thermodynamically. These compositions are stable thermodynamically. It means that if you heat them up, they melt congruently. It means that they will not transform until the melting point. Some of them are stable. This is not the reason that were not discovered before, because there are so many of them. Okay, and they are stable. Maybe they're difficult to make. Not at all. They are very easy to make. When I published the paper, 2 days later, people repeated my experiments. It was very easy to do. So you can make them by many manufacturing technology. You can cast them, you can rapidly solidify them. Single crystal ghost, electron deposition, CVD, PVD. Any method you use to produce any material you can use, you can make quasi-periodic material. This is not the reason they were not discovered. So, are they made of rare elements? Aha, no, not at all. They're made of iron, aluminum, chromium, copper, titanium. Millions of tons of these elements are used every year around the world. These are very common materials, very common metallic elements. So why is it that quasi-periodic materials were never discovered before 1982? And I want to answer my question. Number one, quasi-periodic materials had to be discovered by transmission electron microscopy because they were very, very small. And then I explained to you, you could take X-ray diffraction, and people took X-ray diffractions of these and received rings, and they could not see the forbidden symmetry. Okay, so TM, transmission electron microscopy. So you may say, okay, big deal. There are so many thousands of people around the world doing transmission electron microscopy. Why you? Okay, because you have to be a professional. Now, of the very many thousands of people who do electron transmission microscopy around the world, very few become professionals for different reasons. Number one, you have to invest a lot of time on the electron microscope to become professional. Number two, you have to study the theory. You have to know the theory and practice to the extent that you can teach PhD students transmission microscopy, which I did. And it is expensive. In many places, when you work on the electron microscope, you pay $100 an hour for the microscope. And therefore, many professors will tell their students, okay, I'll give you 5 hours on the microscope, take a few pictures, put it on your dissertation, and go measure the thermodynamic properties. The investment on the part of the professor and the investment on the part of the student is very high. And so I can give you a number. Our microscope at the Technion, we always were leading Israel in electron microscopy. We always have the top-of-the-line microscopes, and we throw away or give away the old ones. In 40 or so, 50 years of electron microscopy at the Technion, maybe we made 15 professionals, 15. And they're all around the world managing electron microscopy or teaching electron microscopy. Of the thousand upon thousand of students, 15. So professionalism is rare. And it's not enough just to do electron microscopy. Learning to drive a car doesn't mean that you can race a car. You can participate in racing. Okay. The other thing is tenacity. When the world around you tells you, what are you talking about? What do they teach you at the Technion? Don't you know it's impossible? Tenacity means you stick to your beliefs. And I could do that because I was a professional. And anybody who argued with me was not. And the people who were professionals repeated my experiments and said, hey, this is wonderful. And we were a fast-growing community. So tenacity. Let me give you an example of somebody who didn't have tenacity. There is one person in Europe that discovered the same diffraction pattern before me. How do I know that? His professor told me, and later on, a couple of years ago, I met him. Wonderful scientist. He did his PhD, and years later, his professor looked at the place that his student took. He pulls one plate, he looked at it, my diffraction pattern. He looks at the date before me. Hello, my ex-student, how are you doing? Thank you, professor, how are you? Say, do you know that you saw Danny Shechtman's diffraction pattern before Danny? He said, yes, professor, of course I know. Why didn't you tell me? He said, you know, professor, if I told you, you would want me to stay for 2 more years on my PhD? He filed it. Okay. Tenacity. Be like a Rottweiler dog. I'm talking to the students among you. You see something strange, don't let go. Be like a Rottweiler dog. You bite, you don't let go until you understand what it is. In most cases, it will be an artifact, or it will be something that somebody discovered 30 years ago. But in some cases, just in some cases, you made a great discovery, don't let it go. Stick to it and understand what you have. That's tenacity. Number 4 is believing in yourself. How can you be strong in believing in yourself? You can do that if you are a professional. And with my arguments with Linus Pauling, the great scientist, he was great, but he did not know electron microscopy, and I was an expert, and he lost there. So my message to you students, if you want to succeed in science in your future, you have to have 2 things. Number 1, broad knowledge of science. You have to know the laws of nature. You have to know thermodynamics. You have to know the language of mathematics. You have to know some biology, and you have to know some physics and some chemistry and so on. You have to have broad knowledge of science. But on top of it, develop one peak of expertise. Be an expert in something that you like. And I promise you, if you have broad knowledge of the laws of nature, and you develop a peak of expertise, become an expert in something, I promise you'll have a wonderful career in science. And you can start now. Choose something that you like and become an expert. And last but not least, resilience. My promotions were delayed because Linus Pauling said that Danny Shechtman is talking nonsense. Scientists said, we don't know what the standards of the Technion are. but he would not be promoted in our university. Resilience means, hey guys, everything will be fine. And of course, everything was fine at the end. Thank you very much. I don't know if you have time for questions, please. Who is the master of ceremony?
Ну що, шановні друзі, після такої фантастичної лекції дійсно хочеться трошки так по-філософськи поставити запитання. Прошу, і я бачу Максим Стріха, заступник міністра. Мікрофон пропонується ставити запитання з центрального мікрофону. Maxim Stricha, who is
Professor Shechtman, thank you for your brilliant and exciting presentation. I have two questions, in fact. The first one is, as to the best of my knowledge, Professor Penrose's article on his mosaics had appeared in the year of 74.
Yes.
Have you ever heard about this article before your discovery of the year of 82?
Yes, I knew about Roger Penrose because his Penrose styles were published in Scientific American in a page that was called Mathematical Games. It was in 1975, I think. So I knew about Penrose styles. But I did know about Ellen Mackay, who showed that they have five-fold diffraction pattern in the reciprocal space. By the way, I met Roger Penrose later on several times. He's one of the greatest scientists in our century. Yes?
Thank you very much. It's very, I'd like to say that Professor Penrose had his lecture in this hall 3 years ago. My second question is that really the previous definition for the crystals order plus periodicity is distributed now by the new one, order plus periodicity or quasi-periodicity. Can you imagine probably the next substitution of this definition by a new one, or this one is the very final? That's
okay,
a philosophical question.
Can we have another order? Okay, so you want me to predict the future? Okay. You know, in Judaism, we have a saying that prophecies after the destruction of the temple were given to the fools. So I will not, it's difficult to say. But I do not, you know, maybe there is another order. I will not say that there is no. I don't know what it can be, but nobody imagined quasi-periodic order before. So yes, there may be an order. And by the way, there are several arrangements which are quasi-periodic, not just the icosahedral symmetry is quasi-periodic. There are other types of quasi-periodicity. We do not have time to dwell on that. A real lecture is a whole day lecture with all the examples, so we don't have time for that.
Thank you very much.
So I will not say that there is no other order.
Thank you.
I'll be happy if it is found. Other questions?
Будь ласка, підходьте до мікрофону в залі. By the way, Dr. Shechtman, Maxim Stricha is a brilliant interpreter. He translated into Ukrainian a big paper of Penrose, Dr. Penrose, and it's a very popular paper in Ukrainian.
Right, let me make a recommendation
Yes,
according
please.
to what you say. Don't translate papers to Ukrainian. Learn English. English is not my first language. I speak Hebrew. I know the language very well. I can understand the poetry in Hebrew. I cherish it. But in order to communicate in the world, especially in the scientific world, you have to know English very well. Not because it's the most beautiful language, but because this is the language we use. Okay? you have to know English very well. It's one of the conditions to becoming a very good scientist. And don't publish your papers in Ukrainian.
Thank you,
Publish
Doc.
them in English. It doesn't help you if you publish in any other language. Publish in English in famous journals. This is your future.
Thank you, Dr. Shechtman. It's a challenge for our youth, and now we are in the process of study business English. And I think in few years it will be absolutely equal level with English-speaking countries. Наступне, будь ласка.
Thank you very much once again for your wonderful presentation. I would like to ask you whether do you believe in the possibility of structurizing of molecules in liquids? This is practically the same as very small crystals in solid solutions, so to say.
Right.
Do you know probably this?
So the question is there order in liquids? Correct? Okay. Okay, there are many studies of surfaces of liquids. I know a group in the Ural Mountains, in Yekaterinburg, Sverdlovsk in the past, who dedicate their life to study the structure of surfaces of liquids, and yes, there is order there. I don't follow the science, but yes, there are, of course, there is a short-range order, that goes without saying, but sometimes there's long-range order, especially on surfaces. I cannot say any more about it. I'm not an expert on that.
Дякую, будь ласка.
I'd like to ask you a little bit funny question, maybe. Your seminal paper was published in Physical Review Letters, yes?
Say it again?
Your seminal paper was published in Physical Review Letters, yes? But you got a Nobel Prize award in chemistry, not in physics, yes? Do you know why, for the first?
So the question, why?
Why? Do you know?
Okay.
And are you considering yourself as chemist or physicist?
Okay. So two questions. Question number one, why did I receive Nobel Prize in Chemistry? The explanation is quite simple. The science of crystallography, they decided in Stockholm that crystallography will belong to chemistry. It's a decision that they made. They could have made it differently and sent it to physics, but they decided that crystallography is chemistry. So this is the reason why. I did not expect it in chemistry. In fact, I can tell you that on October 4 of 2011, they announced the names that received the Nobel Prize in Physics, and I was not among the names. So I said, okay, another year, no problem. And then the next day they announced it, but I didn't know that they announced it the next day because I never followed what happens in chemistry. So it was total surprise for me when they called my telephone. Okay, and the other question was, I forget by now. What was the other question?
Do you consider yourself as a physicist?
Oh, no, I am a material scientist. But listen, fellows, the world of science is not clearly divided between physics and chemistry and biology. It is all the same thing. It's all material science, right? Any way you look at it. And when I was younger, we sent proposals to chemistry, to physics, to material science, to biology. Now everybody does material science. It's all the same. And the rules are the same. So yes, we still have a department of chemistry and department of physics, but really it's all merging. I do everything. Yes, other question.
Well,
yes,
I would like to thank you for the lecture, and the question is, are there any applications of quasi-crystals based on their specific structures?
On?
Are there any applications of quasi-crystals based on their specific structure?
Okay, so applications.
Yes.
All right, so let me say a few words about application. If you find, if there is a new class of materials that is found, then people first study the properties. In order to find applications, you have to know the properties of the materials. And properties of quasi-periodic materials were studied vastly. And thermodynamic, physical properties, optical properties, magnetic properties, electrical properties, you name it, properties was studied of each and every one of the many quasi-periodic materials. In general, they have certain properties which can be useful. One is low heat conductivity. They're not the excellent insulator, but they're good insulators for heat. They conduct electricity, but they behave the opposite of superconductors. When you cool down superconductors, their resistivity goes to 0. When you cool down quasi-periodic material, the resistivity goes to very high value. Not to infinity, but to a very high value. They just behave differently. These are superconductors, these are quasi-periodic material. They are usually hard materials, they are brittle. You cannot use them as structural material, but you can use them as coatings. They have interesting optical properties, interesting magnetic properties, and so there are some uses of them. Let me give you a couple of applications. The first product ever to emerge was frying pans coated with quasi-periodic materials because they have very low surface energy, and consequently, the omelette that you make, and it doesn't stick. Like Teflon, it doesn't stick. But unlike Teflon, you cannot scratch it, so because it's hard. So if you cut an omelette in a Teflon-coated frying pan, you will destroy the Teflon, which is bad, it's poisonous. And if you cut with a knife an omelette which is made on quasi-periodic materials, you will destroy the knife because it is so hard. So this was the first one to be used. And then there were other applications. One of the most prominent and interesting applications is like strengthening particles for stainless steel. Now, there is a company in Sweden called Sandvik. Sandvik because their headquarters are based in Sandviken, a city in the north of Sweden. And they produce a stainless steel, which is the strongest steel I know, which is strengthened by quasi-periodic particles. It's a fantastic steel, and many of you use this steel, even though you don't know it, because they use them for shaving machines. So this steel that touches your face is made in by many companies from that steel. It's hard, it's extremely strong. I asked them if it had some military applications. They said, "What are you talking about?" I said, "I never asked." So this is just one example. Okay, other, yes, ma'am.
I would like to ask about the stability of the quasi-crystals.
Say it again.
Are the quasi-crystals stable or not stable structures? And does this question of stability depends on the size of the quasi-crystal?
Okay.
How large quasi-crystals?
Okay. So there are two questions. Are they stable? Most of them are not stable. Some of them are stable. Stable means that they, as I mentioned before, they melt congruently. They do not transform until the melting point, okay? Most of them are ternaries, the stable ones, and some of them are binaries, binary composition. So this is about stability. And the other question? Say it again.
Будь ласка, наступне питання.
What was the other one?
And what about the seven-fold symmetry?
No, wait, what was the other question? of this lady?
Вибачте. У вас було два запитання. Яке було друге?
Does anybody remember?
Also
What was
about
the second one?
stability, does the question about
but
stability
size.
depend on the
Okay,
size?
it does not depend on size. Right. You can have, now they grow single crystals, single quasi-periodic crystals, any dimension you want. It just takes time. But you can grow them to be like this. Right? Doesn't depend on size. It's a good question, but it doesn't depend on size. Okay.
And what about the possibility of not five-fold symmetry, but seven-fold symmetry or higher symmetries in quasi-crystals?
Right. Yes. I challenge you to find it. It's there waiting for you. Okay. Other questions? I'll stay here.
Є, будь ласка.
Hello, thank you for the presentation. And I want to ask you, have you ever thought about the introducing of scholarship for the talented student, which may have, for example, your name, to study abroad? Because here in Ukraine, we do not always have an ability to improve our knowledge in some fields of studies.
Okay, so the question is, did I ever think about establishing a scholarship on my name? Okay, I can tell you that there are scholarships on my name, that I didn't pay for it, but other people pay for that. But you came up with an important question. How do you get to be educated in a good university for a postdoc or something like this around the world? But this question is true in every country. And many people write to professors, do you have a position for me? I can tell you that I receive one a day, mainly from India, of students who want to come to my laboratory. And regretfully, my answer is negative because they don't hire any more students now that I have retired. I retired this year. So just write letters to professors in your field and you'll find a position. There's a lot of money available for foreign students around the world. The United States, England, France, Germany, anywhere. Israel too. Okay, other questions?
Наступна, будь ласка.
Dr. Shechtman, thanks a lot for your really inspiring lecture. I'm not a material scientist, but it was really, really amazing. Especially thanks a lot for your advices.
I think that people don't hear it.
Okay, yeah, thank you for your advices. That's really, really helpful, yeah, and inspiring again. So I have such a question. Again, I'm not a material science, but I got the main idea that the biggest problem to discover this quasi-periodic crystal was its size. Yeah, I mean, X-ray crystallography was too rough to see these crystals. Yeah, does it mean that this size of quasi-crystals is generally smaller than regular periodical crystals? Does it mean that these quasi-periodic crystals always smaller, or maybe they growing, let's say, more difficult? Yeah, I mean, is periodic structure has any energetical benefits or more, let's say, energetically effective than quasi-periodic structure?
Okay, you didn't listen to what I said before. What I said before is you can grow crystals like this. So,
yeah, but before,
no problem.
Before your discovery, there was no such crystals. Yeah, I mean, it takes some efforts, additional efforts to grow bigger crystals.
Same thing.
Same thing. So
yeah,
it doesn't matter.
No,
yeah,
it's the same thing.
Okay.
There's nothing different. And when you look at them, you cannot tell the difference. You say a crystal of aluminum, a crystal of aluminum manganese or aluminum manganese silicon. You look at them, you cannot tell the difference. This is like this. This is like this. It just takes time to grow them. They are simple intermetallics. That's it. But they have a very specific structure. These are intermetallic with very specific structure. That's it. Nothing is mysterious about them.
Okay, thank you very much.
Okay, other questions?
Наступні запитання? Не бачу.
Okay.
Oh, Dr. Shechtman, thank you very much for your brilliant lecture. And
Thank you all for listening.
And in the memory of this great event, let me present you this lithograph pictured another famous chemist, Dmitry Mendeleev. Dmitry Mendeleev was our professor in the beginning of last century, and in this lithograph he pictured as the head of the exam commission, which was located just in this hall, due to this hall named Mendeleev Hall. So, okay. Let me present you. Okay. Dr. Shechtman, thank you very much. We wish you a great success and many other discoveries. And we will be happy to meet you again at our university. Thank you very much.
Thank you very much.